Gallium Nitride, or GaN, has been doing the rounds in recent years, especially when it comes to consumer electronics like phone and laptop chargers, and it may seem like just a bit of a buzzword, but it's a whole lot more than that. GaN is a semiconductor material just like silicon, and it has some special properties that give it a significant edge over silicon in certain applications. But how does changing the material that a single component is made out of allow every other component in a power supply to get smaller? Let's go through them one at a time to find out. First off, I strongly recommend that you watch my previous video on switch mode power supplies, if you haven't already, as that goes over the purpose of all the components we're going to be looking at today, and I won't be repeating much from that video. Now let's start by taking a quick look at both power supplies to see what stuff jumps out. We can immediately see that both power supplies have an open frame form factor, meaning they're not in any sort of enclosure. Of course, this form factor is only really available for industrial power supplies like these, because if phone chargers were like this, people would probably die. Despite appearances, both of these power supplies are actually very similar electrically, with only a few small differences that we'll get into as we go through the components. The most obvious difference between the two power supplies is the size, with the gallium nitride power supply about a third of the volume of the silicon power supply, and the difference in weight is about the same. Now I'm sure there's quite a few of you screaming at your screens right now saying, "What's the point of this video? I already know it's just to do with switching frequency." And indeed that is by far the biggest contributor to the difference between these two power supplies. But things aren't as simple as just doubling your switching frequency and halving the size of your power supply. There's a lot more to consider, and that's what we'll be getting into shortly. Both of these power supplies are rated for about 50 watts, to keep the comparison as fair as possible. One major contributor to the difference in weight and volume is the fact that the silicon power supply has two large heat sinks. While the GaN power supply does have this little shield thing, this is more here for blocking EMI, and its contributions to thermal performance are fairly minimal. Of course, the absence of any heat sinks on the GaN power supply indicate that it must have much lower losses than the silicon supply, and indeed it has a much higher efficiency. So, speaking of efficiency and losses, let's not just take the manufacturer's word for it, let's test it ourselves. So here's my setup for measuring the efficiency of these power supplies. You can see here I've got this not at all overkill Zimmer power analyzer for measuring mains input and DC output power of our power supply. And then I've also got this Kikasui electronic load, which we can use to vary the amount of power our supply is having to, supply. Big thanks to Telonic for kindly providing these, and some other equipment used in this video. You may have noticed there's quite a few wires connected to the power supply. This is because to get good efficiency measurements, we need Kelvin voltage sense connections, which means we're measuring the voltage directly at the input and output, so that any voltage drop across the cables going to the load and from the supply don't skew the measurements. Our main supply comes from this socket, into which we insert this plug. Our power supply is now connected to the mains, which we can see when we look at the screen of the power analyzer. We can see my main supply voltage is about 247 volts RMS, which is quite high. And even though the electronic load is turned off, this power supply is still drawing 1.2 watts. That means if I just had this power supply always plugged in but never actually supplying anything, it would cost me £4 or £5 a year in electricity usage. That's pretty shit. You can see this power analyzer also tells us some other stuff. We've got the power factor, which is derived from the real power divided by the apparent power. There's the reactive power, which is to do with that. And then we can even click on this to get even more numbers. But that's a bit too much for one video. Moving over to group 2, which is our output, we can see we've got an output voltage of just over 12 volts with no load. And we can also see that when I do turn on the load, this voltage drops quite significantly, showing that this power supply has quite poor regulation. And this is something we'll look at later on. But the main thing we want to measure with this power analyzer is efficiency, and we can get that by clicking on this button, and then clicking a few more buttons. So you can see here we've got the efficiency, which is 0.85, that means 85%, and the losses about 8.5 watts. These vary as I change the load, so right now I'm drawing 4 amps. If I drop that down to 1 amp, you can see our efficiency goes down quite a bit. We're now at about 78%, and our losses have also gone down. This power analyzer also allows us to monitor the voltage and current waveforms, just like an oscilloscope. And here you can see in red, the mains voltage is nice and sinusoidal, and in orange, the current draw of the power supply is that typical spiky full bridge rectifier current waveform, as we saw in my video about active power factor correction. Anyway, here are the efficiency curves of both power supplies, showing what proportion of the energy we put in turns up at the output, over a wide range of power levels. Clearly the yellow line is always higher, showing that the GaN power supply is always more efficient, but I think we probably all expected that, so let's delve a little deeper. We can see that the efficiencies at high load, so between 10 and 50 watts at the output, are fairly close, at least closer than they are at lower power, with the silicon power supply showing a peak efficiency at maximum load of 85%, while the GaN reaches 92%. The change from 85 to 92% may not sound like a huge difference. They're both quite high numbers, but that's almost halved the loss, so less power is wasted, less heat is produced, and we don't need as much cooling. And of course, this difference in efficiency gets much larger at lower power, where the GaN power supply is up to 3 times more efficient, meaning for the same output power, we have to put in 3 times more power for the silicon power supply. Now you can probably guess why this is, based on something we saw when we were first looking at the power analyzer, the no-load or idle power consumption, how much power the power supply draws with nothing connected to the output. The power supply can never draw less than this, and at light loads, these losses that are always there will be the primary factor determining the overall efficiency. The no-load power consumption of the silicon power supply is 1.2 watts, whereas for the GaN power supply it's around a tenth of that, 110 milliwatts. The silicon power supply hits its minimum possible losses at 1 watt, and below that the losses reduce no further, whereas in the GaN power supply they continue to reduce, which is why its efficiency was so much higher at light load. Moving over to the other end of the graph, we can see a few squiggles in the curves. You might think these are just dodgy data points, but that Zimmer power analyzer is not dodgy, and neither am I. These are caused by the controller of the power supply changing something. It could be switching frequency, maybe entering a burst mode. There's quite a few tricks these controllers do to optimize losses and efficiency over a wide operating range. The last thing to look at is another thing we saw when initially looking at the power analyzer, the output load regulation. This is how much the output voltage changes under load, almost always dropping at high load. Now, we can immediately see that the two power supplies have slightly different output voltages, so to make the comparison between load regulation clearer, let's look at the normalized output voltage. That's how much it reduces from its value at no load. Crikey! The output voltage of the silicon power supply drops off a cliff above 5 watts, losing about 90 millivolts? Yeah, it's not that bad to be honest, but once again, the GaN power supply is much better, dropping only 10 millivolts at full load. Now, I will admit this has nothing to do with the gallium nitride and everything to do with good design practice, but it's still very interesting to see, and we'll discover the one simple change that has given this huge improvement in regulation later on. Thinking of making your own power supply? You'll need PCBs for that, and the best place to get them is JLCPCB. With over 19 years of experience manufacturing affordable and reliable PCBs for engineers and hobbyists alike, JLCPCB have got you covered. Ordering your PCBs is as simple as drag and dropping your Gerber files onto their website and selecting any options you'd like. For example, on this board I've made for a future video, I selected a thinner than normal PCB, and also gold plating for the bling. Once you've placed your order, you won't be waiting long, thanks to JLCPCB's rapid manufacturing and great shipping options. So, when you next find yourself in need of PCBs, make sure to get them from JLCPCB using the link in the video description. Now let's start looking through the components, starting with... The mains rectifier is actually the component with the single biggest difference in size between the two power supplies. Here's the rectifier on the silicon power supply, and you can see it's already fairly small relative to the size of the whole power supply. But if we move over to the GaN power supply, it has a tiny surface mount rectifier hiding underneath the input filter. And this is actually less than a tenth of the size of the one on the silicon power supply. So presumably it must be a lot more efficient for us to be able to shrink it down so much. Well, if we measure the forward voltage of one of the diodes in each rectifier, we can see there's actually not really any difference in forward voltage, which means the losses for a given current will be basically the same. So of all the components, it's a shame this is the one we had to start with really, because it's probably the most boring. The main reason it can be so much smaller on the GaN power supply is really just because it's too big on the silicon power supply. Another interesting thing to note is that the forward voltage of diodes drops as they heat up, meaning that this smaller package, which will heat up more, might end up being more efficient, because up to a point you could say that diodes like to run hot. They'll be more efficient at higher temperatures. If the temperature increases too much, diodes start to become bad at blocking, with higher and higher leakage currents, leading to significant loss due to current flowing when it shouldn't. but that's not too much of a concern for these rectifiers, as they won't be getting excessively hot. They will, however, heat up a bit, and as the losses on both rectifiers are pretty much the same, but the one on the GaN power supply is much smaller, we'd expect that one to get quite a bit hotter, and indeed that is the case, though it's not immediately obvious. Here's the little rectifier of the GaN power supply, and it's got itself up to about 62 degrees at full load. However, when we take a look at the silicon power supply's rectifier, it's actually a little bit hotter, which doesn't really make sense. It has a much bigger surface area, so should be able to dissipate its losses more effectively and therefore be cooler. Those of you who are on it have probably already spotted the cause of this discrepancy. On the silicon power supply, the mains rectifier is right next to the hot heatsink of the primary MOSFET, which is over 70 degrees. This is heating up the rectifier, making it look much hotter than it would otherwise be if mounted in thermal solitude like the GaN power supply's rectifier. To prove this, I mounted the heatsink onto a much bigger heatsink with a fan to suck out all the losses of the MOSFET, and, as expected, the rectifier temperature dropped dramatically to just 35 degrees. Of course, if the rectifier was getting heated up by the heatsink, then it's almost certainly now being cooled by it, so in reality, the rectifier's true temperature, were it to be alone, would be somewhere in the middle. Moving on from the component that's shrunk the most to the component that's shrunk the least, the input capacitor. Why is this still so big? Well, it's still got to deal with 50 Hz mains. Filling in the gaps where the input voltage is too low requires a set amount of energy, and there's not really anything we can do to get around that. Now, it is clearly still a bit smaller. In fact, it's almost half the capacitance, 56 microfarad versus 100 microfarad on the older silicon supply. And what that means is that for a given power output, there's going to be more voltage ripple on the smaller capacitor of the GaN power supply than on the bigger capacitor on the silicon supply. Bigger voltage ripple might sound like a problem, but if you design your power supply well and have a fast enough controller, you can completely eliminate it from the output. This is done by constantly and very rapidly varying the duty cycle, essentially turning up the gain of the converter as the voltage across this capacitor drops. And then when the mains reaches its peak and the capacitor gets charged back up, the controller then very rapidly reduces the duty cycle back down so that the output voltage remains constant throughout. An easy way to confirm that this GaN power supply does indeed have much faster control is to take a look at the step response, how much the output voltage drops when we suddenly start drawing current, before the controller notices and turns up the duty cycle to compensate. The output of the GaN power supply returns to within 1% of its original value in 600 microseconds, whereas for the silicon power supply this takes 5 milliseconds, more than 8 times longer. Now, there are several things that cause this, like a larger output capacitance, but a slower controller certainly plays a significant role. Another thing that allows this capacitor to be smaller than this one is that, well, it's a much nicer capacitor, a Rubicon to be specific. This means despite its smaller size, this capacitor can handle more low-frequency ripple current than this one, because it has a lower ESR. We'd typically expect higher ESR in capacitors that are physically smaller and lower capacitance, but Rubicon makes some good shit, and this is certainly one of those shits. For more information on ESR and capacitors in general, check out my video comparing every type of capacitor used in power electronics. Next up is more capacitors. Hiding on the back side of this PCB are 7 surface mount multi-layer ceramic capacitors, or MLCCs. Surface mount ceramic capacitors are very common in modern switching circuits because of their excellent high frequency performance. In this power supply, the reason they're placed here is to get them as close as possible to the star of the show, the Gallium Nitride transistor, which lives on the opposite side of the PCB. Having the capacitors really close keeps the stray inductance as low as possible, which is crucial for minimizing any overshoots that might happen when switching. The next component we're going to look at is another one that's quite hard to see. Sitting between the main input capacitor and the multi-layer ceramics that we just looked at is an inductor. That may seem quite counterintuitive because we've just been talking about how there needs to be as little inductance as possible between the capacitors and the switch. Well, because gallium nitride lets us switch so fast, the actual capacitance required for the flyback converter, the DC to DC part of the power supply, is pretty small. So small in fact that those ceramic capacitors provide pretty much all that we need. And as they have such a good low inductance connection to the transistor, there's not really any need for a low inductance connection to the main capacitor. So this inductor's here to block that high frequency current from making it to the capacitor, because it would just introduce additional losses and potentially shorten its lifetime. It also helps reduce EMI of the power supply by acting as a filter and keeping those high frequency currents contained in this small portion of the power supply. Right, it's now time to move on to what we all came here to see, the gallium nitride transistor. First off, it's pretty obvious that this is much smaller than the silicon transistor on the old power supply. Once again, this is partly due to advancements in packaging, but it's also helped by the fact that for the same size of die, a gallium nitride transistor will have a lower on resistance, meaning that a transistor rated for the same current will be smaller. This is thanks to GaN's higher electron mobility. The main advantage of GaN, however, is its switching performance, which is much better than silicon's for quite a few reasons that deserve their own video, but here are a few key points. Gallium nitride transistors have very low gate charge compared to silicon transistors. Lower gate charge makes it a lot easier to turn the transistor on and off quickly, with fewer losses in the gate drive circuit controlling the transistor, and fewer negative impacts resulting from parasitics due to much lower gate current. GaN transistors also have no body diode, which means no reverse recovery to worry about. This helps to minimize overshoots on very fast switching transitions. Miller capacitance is also much lower in GaN devices, simplifying the gate drive circuitry by eliminating the need for negative voltages and active Miller clamping. A good way to quantify just how much better these devices are is to calculate something called figure of merit, which is the gate charge, so how hard it is to turn the transistor on, multiplied by the on resistance, so how on it is once it's turned on. The figure of merit of this GaN transistor is almost 100 times lower, which is better, than the old silicon one, showing that not only is it more on when it's on, but it's also much better at turning on and off. This ultimately means that, despite switching several times faster than the silicon transistor, the overall losses will still be a lot lower. Now moving on to the component that's got me most excited, the transformer, which in the case of flyback converters like these isn't actually a transformer, it's a coupled inductor. But of course you already knew that from the previous video on switch mode power supplies. Here's the coupled inductor of the GaN power supply, and you can hopefully tell it looks quite different to that of the silicon power supply, and not just because it's not wrapped in yellow tape. This is a planar transformer, which means it uses tracers on a PCB as windings, and there's no actual wires. How cool is that? We can clearly see that this PCB is a lot thicker and more solid than the other two PCBs on the power supply, and that's because it's almost certainly stuffed with layers to fit in enough turns on the primary and enough copper on the secondary to keep the inductance high and the losses low. But what's the point of the planar magnetics anyway? Haven't we been doing just fine with wire-wound transformers for over 100 years? Well, yes we have, but there's a few problems with them that planar magnetics do a good job at solving. First of all is manufacturing. Winding conventional transformers is very time-consuming and costly, and there can be very big inconsistencies between transformers, even off the same production line, because every time you wind the transformer, the wire is going to fall into a slightly different place, meaning slightly different characteristics. In contrast, PCB manufacturing is very cheap, very consistent and very repeatable, meaning every single planar transformer off the same production line will have pretty much identical characteristics, which is of course very helpful when you're trying to optimize something as much as possible, as is the case with this gallium nitride power supply. The fact that using a PCB allows us to define exactly where the windings will be positioned in the transformer isn't just good for consistency, it also allows us to optimize the transformer in several ways. First of all, we can manipulate where the windings are relative to the core. Specifically, we can keep them away from the air gap. What air gap? The air gap is a literal gap that we add into the core of inductors to increase their reluctance and the current at which they'll saturate. Saturation is basically when you max out the amount of magnetic flux the core can hold, and the inductor stops behaving like an inductor. But why do we need to keep the windings away from this air gap? Well, it's because the magnetic field passing between the top and bottom halves of our core doesn't just flow in a nice straight line. We have something called fringing at the edges, which is where the magnetic field kind of spills out. And you can see at these edges of the air gap, the magnetic field is overlapping with our windings, which leads to all kinds of problems, generally meaning higher losses in those parts of the windings and lower overall efficiency. What we can do with planar magnetics is move that air gap to one end of the core like this, and we can then sit our PCB below that gap, keeping all of our windings nice and far away from this fringing flux. And we can see that's exactly what Cosel have done with this coupled inductor. There's the PCB containing our windings shoved right the way up to the top of the core, and the air gap, which is very small and hard to see, is down at the bottom on the opposite side of the core. Very nice. A second thing that control of the windings positions allows us to do more easily is interleaving. This is where, instead of having all our primary windings and then all of our secondary windings, we mix things up a bit. This can range from a simple primary sandwich all the way up to a full-on zebra. Typically, people tend to stay closer to the sandwich style due to the fact that every time we have primary next to secondary, we need some isolation, which takes up precious space. A key advantage of interleaving in a flyback converter like this is that it provides better coupling between primary and secondary, reducing something called transition loss. This is loss in the core of the inductor caused by the sudden change of magnetic field distribution as current very rapidly stops flowing through the primary and starts flowing through the secondary. Interleaving the windings reduces how much the magnetic field will change during this transition. Related to this is also lower leakage inductance, which represents energy stored in the primary winding that can't be transferred to the secondary because of poor coupling. That energy needs to be dissipated into snubbers, so it gets wasted every time the switch turns off as losses. The next thing we're going to look at is the output diode, which, in the case of the GaN power supply, isn't actually a diode, but rather a MOSFET. This is because it uses something called active rectification, or synchronous rectification if you want to use more syllables. Active rectification is massively more efficient than conventional passive rectification using a diode, and I reckon this is probably the single biggest improvement in efficiency and reduction in losses between the two power supplies. The MOSFET's controlled by this little 6-pin chip that just needs a few extra components around it to work. No need to connect to the controller on the primary side, which is handy for keeping things simple. Essentially, this controller just turns on the MOSFET whenever a diode would be on, and because low voltage MOSFETs have very low on resistance, the losses for a given current are much lower than that of a diode. We can quite easily work out how much of the efficiency improvement between these two power supplies is down to this active rectifier. We have a full load output current of 4 amps, and let's assume the diode is on for 50% of the time, meaning it will see 8 amps. Conveniently, this is its rated current, so the datasheet tells us clearly what the forward voltage will be, 0.58 volts. The losses in the diode are just that voltage multiplied by 8 amps, and then halved because it's only conducting half of the time. That gives us 2.32 watts, which is over a quarter of the total losses. In comparison, the losses in the MOSFET are given by the current squared multiplied by the on resistance, which is a tiny 5 milliohms, giving an average loss of just 0.16 watts. This means the efficiency improvement from this change alone is over 4%, and the overall difference between the efficiency of these two power supplies is 7%. You've probably already noticed, but next to the output MOSFET are some more multi-layer ceramic capacitors, and in fact there's even more hiding behind it on the other side of the PCB. Once again, these are here to deal with the high frequency current of the flyback converter, just like on the input. And to be honest, there's not a lot more I can add. They're doing the same job as the ceramic capacitors on the primary. And speaking of doing the same job, if we once again look very closely into the bowels of the power supply, we can see a sneaky inductor hiding away. Once again, this is doing the same job as its counterpart on the primary side, blocking those high frequency currents from making it to the main output capacitor. Both power supplies actually have an inductor between different output capacitors, so appear almost identical looking at the schematics, until you take a closer look at the types of capacitor used. In the GaN power supply, the inductor sits between the ceramic capacitors that are dealing with high frequency and the main polymer output capacitor, which is dealing with lower frequencies. This inductor's helping the two types of capacitor to only have to operate over the frequency range that they're best suited for. In contrast, all 4 output capacitors of the silicon power supply are the same electrolytic capacitors, so the inductor isn't really performing the same job despite looking the same on the schematic. And that's because the silicon power supply doesn't have any capacitors that are good at high frequencies. So really, all this output inductor's doing on the silicon supply is sparing the final output capacitor from the high frequency torture that its buddies are having to endure on the other side of the heatsink. We can see this quite clearly at high load. The 3 capacitors before the inductor are more than 10 degrees hotter than the one after the inductor. While this temperature difference isn't entirely down to the high frequency current, it's certainly a contributing factor. Now, I already briefly mentioned this, but the main output capacitor of this GaN power supply isn't electrolytic, but rather my favourite type of capacitor, polymer. Polymer capacitors are basically drop-in replacements for electrolytic, and are better in every way. They have a solid electrolyte rather than the liquid in conventional electrolytic capacitors, which increases their operating temperature and lifetime, because solids don't really evaporate. They also have much lower equivalent series resistance, meaning they can handle higher currents without heating up and can operate effectively at higher frequencies. In contrast to this, the silicon power supply uses 4 standard electrolytics. Using multiple capacitors in parallel is mostly just done for packaging, and also tends to give lower overall ESR, though I imagine all 4 of these in parallel probably still gives a higher ESR than this single polymer cap. And because of the cooling that's needed for the output diode on the silicon power supply, these output capacitors have ended up right next to the hot heatsink, which will heat up the capacitors, drying out the liquid electrolyte over time, so these will almost certainly be the first point of failure in this power supply. In contrast, the GaN power supply has its output capacitor decently far from any of the heat sources, plus because it's polymer, it's rated for a maximum operating temperature of 125 degrees, that's 20 degrees higher than the electrolytic capacitors of the silicon power supply. The overall capacitance of the GaN power supply is about a third of that of the silicon one, thanks to the much higher switching frequency, requiring less energy storage to smooth out the shorter, more frequent pulses from the transformer. While the capacitance has gotten 3 times smaller, the total volume of the output capacitors has shrunk by more than 10 times. This is because the GaN power supply's output capacitor is rated for just 16 volts, which is fine because it's only a 12 volt output. The silicon power supply's capacitors, however, are rated for 35 volts. Why have they done that? Well, it's most likely something called derating, which is when you overspec a component with the aim of achieving a longer lifetime. The idea being that, as the capacitors were designed to last a certain amount of time at their maximum voltage, they should survive quite a lot longer at well below half of that. Similar to how, if I train for a 5-kilometre run, I'll get fit enough that I can easily walk 15 or 20 kilometres, because walking is usually easier than running. Now it's time to head back to the input, to see how both of these power supplies prevent high-frequency switching noise from making it onto the mains, and for that they of course have an input filter. Both power supplies have a common mode choke, though this is significantly smaller and simpler on the GaN power supply, which just uses a small ferrite toroid with 5 turns on each side. Both power supplies also have at least one X capacitor which sits across the line between live and neutral. The silicon power supply has 1, 2, 3, whereas the GaN power supply has 1 and it's smaller than just one of the silicon power supply ones. The GaN power supply needs less filtering because of the higher switching frequency. This is twofold as the impedance of the filters gets higher at higher frequencies, meaning for a certain amount of blocking you need a smaller filter for a higher frequency. And also the regulations are less strict at higher frequencies because the inductance of the wiring in the building and beyond will act as additional filtering at such high frequencies. The controller of the GaN power supply also has something called frequency jitter, which constantly changes the switching frequency a little bit to spread out the switching noise so that there isn't just one big spike at a particular frequency. Input protection is probably where the 2 power supplies are most visibly similar, with both having a reddy browny coloured through-hole fuse and a black NTC thermistor for inrush current limiting. The GaN power supply has no earth connection, meaning there can't really be any proper Y-caps like the silicon power supply has, connecting various points of the power supply and earth. But it does still have one Y-cap between the positive of the input capacitor and the negative of the output, so essentially across the isolation, a bit like this Y-cap on the silicon power supply. Cosel have gone for one of these really nice surface mount Y-caps from Murata, which is really cool to see because they're a fairly new product. Things like this make it clear that this power supply was definitely designed by passionate engineers, because there are so many nice component and layout choices throughout. One example of the nice design I've seen is these voltage sense tracers that go right the way to the output connector, which helps this power supply have excellent load regulation, because the voltage the controller sees is the voltage on the output, not the voltage a bit away from it, as is the case with the silicon power supply, where the controller is blind to voltage drops beyond the measurement point. Just like my previous video, I won't really be going into detail on the controller circuit itself, as that definitely deserves its own video, which will come one day. Now that we've gone through all the components, let's do a really speedy summary of how and why each one has shrunk. The input filter is smaller and simpler on the GaN power supply because higher switching frequency requires less filtering. The mains rectifier is oversized on the silicon power supply due to its age, whereas the GaN power supply uses a modern surface mount one which is much smaller. The input capacitor is halved in size and capacitance, which we can get away with thanks to GaN's higher switching frequency enabling faster control. The primary side switch of the GaN power supply is of course Gallium Nitride, which has both lower on resistance and lower switching loss, needing less cooling, meaning it can be smaller. The transformer, which is actually a coupled inductor, is a quarter of the size on the GaN power supply because of the higher switching frequency, and it's also planar, so that's cool. The secondary side switch has been swapped from a diode to a synchronous MOSFET, which has much lower conduction losses but does require additional control. And finally, the output capacitor is a tenth of the size of those on the silicon power supply. Because it's rated for lower voltage, it has less parasitics and it's operating at higher frequency. All in all, this Cosel GaN power supply is really nicely designed. Clearly a lot of thought was put into it, which is really refreshing to see in a world of cost cutting and planned obsolescence. Big thanks to Relec Electronics and Cosel for providing one of the power supplies for this video. Relec are experts in power supplies, displays and industrial computing, and offer products and personalised support to businesses and OEMs in the UK. And Cosel? Well, they make these lovely power supplies and quite a lot more. Hopefully we'll be able to take a look at more of their products in the future. And that's it. I hope you enjoyed this video. I know it's been a bit of a mishmash, but there was just so much to cover with these power supplies, and I really wanted to fit as much as possible into this video. Now, it's not something I ask often, but please consider subscribing. I'm trying to hit 100,000 subscribers before the end of June, and it'd be really great if you could help me out. Now, I won't take any more of your time. Until next time, bye!